Let us now discuss parameter estimation. So this is the problem where I have a sample of n observation, and I think, my prior hypothesis that these are IID draws from a certain probability distribution that depends on a certain parameter theta. Okay? And then the question I want to ask is what is the value of the parameter theta? And so the best, very simple answer is that one should find the parameter theta which is more likely. Okay, so the maximum likelihood estimator. So the maximum likelihood estimator is also called MLE. So is the value of the parameter, it is a function of the sample that maximizes the probability of the sample given theta and maximizes over theta. Okay, so the probability of the sample given theta is just the product of an I from 1 to n of f of xi given theta. But this can also be written so this thing can also be written as E to the sum of an I from 1 to n of log of f of xi given theta, so which can also be written as, if I introduce the type or the empirical distribution, can also be written as e to the n times the integral of dx of x times log of f of x given theta. So, and this, as usual, can be written as e to the minus n times the DKL of the sample from f of x, f, so the distribution f theta, minus n times the entropy of, say, the differential entropy of the time. Okay? So, but this is a constant, does not depend on theta. So, essentially, the maximum likelihood estimation corresponds to finding, if you want to maximize this, then you want to find a theta that minimizes the distance of the type from the parameter family. So, which is again a large deviation problem if you want. It's the same problem that we have discussed before. So again, if you have your space of probability distributions, then this parametric family will be a manifold in this space, which is parameterized by theta. And then somewhere you have your sample in this space, And what maximum likelihood tells you is that on this manifold you should find a point theta hat that is closest to the sample in terms of Kullback-Leibler divergence. Okay, so did say there is another way in which you can write this, which is essentially using instead of the likelihood, the log likelihood. Okay, so the log likelihood. So let me, per point, let me define this function L of theta and x as 1 over n sum over I from 1 to n of the log of f of xi given theta. So it is clear that this is so this probability here is nothing but this is equal to e to the n times the log likelihood of theta and x, and so this maximization can also be written as of this function, okay, of the log likelihood. Okay, why do I introduce this function here, this object here? Because essentially, when n goes to infinity, this this will satisfy a law of large numbers because these objects are finite and are finite variance. So that I expect that for n going to infinity, this converges to a function of theta, which is not random. Okay. Okay. So very good. So now, however, this point theta is clearly a point that depends on the sample. So if you imagine the situation where you have, say, a real, imagine that you have, that you draw samples from this distribution with a certain parameter theta 0, which is the true parameter. Then the samples will be somewhat distributed around this point. The possible samples can be around this point, and as a result, the theta hat will be a random variable that depends on the sample that is generated. Okay, so this if I draw many samples, then I should have the distributions of values of theta around theta naught, around the true distribution. Okay. So what I would really like to know is about the true distribution, but actually, in particular, I would like to understand how much the maximum likelihood estimator is far from the true distribution. But well, this I cannot do because I don't know what is the true distribution. What I can do is to understand what is the probability distribution of theta hat of x. So what is the probability? In other words, I can think in Bayesian terms, And I can say if I have a prior distribution over theta, then I observe the sample x, and I can estimate a posterior distribution theta, given the sample. And this will give me essentially a distribution, what is the distribution of theta that I should assume after I see the sample. Okay? So let's see what is the form of this probability distribution, or the probability of theta given the sample. So this is just given by the law, by Bayes' theorem. No? So this is just so it's just the probability of x given theta that I'll write as e to the n times n of theta and x times the prior probability of theta divided by p of x. Well, p of x is just the integral of the theta of whatever is in the numerator. Okay, e to the n times n of theta prime and x times p0 of theta prime. Okay. Now you see that when n is very, very large, then this is a distribution that is very much concentrated around the maximum of L, or around the maximum likelihood estimator. Okay? And so what I can do in order to estimate this probability is to expand the likelihood around the maximum likelihood estimator. So what I'm going to consider now is just the case where we have one single parameter in order to keep the mathematics simple. But then we are going to see how this extends to the case where the parameter, the family depends on more than one parameter. So you have a d-dimensional vector of parameters. Okay, so in the case where you have just one parameter, you can write that the likelihood, this log likelihood, is essentially equal to the likelihood of the maximum at the maximum minus, I'll write it as in this way, gamma over 2 times theta minus theta hat squared plus higher order terms. Again, the reason why I write it in this way is, so here is gamma will be minus the second derivative or the second derivative of the likelihood, log likelihood computed in theta hat of x. So, because well, what I expect is that the likelihood is maximal at theta hat, so I expect this gamma to be positive. So, so if I use this when I can estimate this integral here with the saddle point method. So this integral at the denominator will be essentially square root of 2 pi over n times gamma times e to the n times L of theta hat and x bar x times p0 computed in theta hat. Okay, this is the integral below, and so you see that if I substitute this expansion here in the numerator, then L of theta hat cancels, and I just have that this is square root of n times gamma divided by 2 pi times e to the minus n gamma over 2 times theta minus theta hat squared. And then, well, there is the p0 of theta divided by p0 of theta hat. But to leading order, essentially, I mean, in the region where this the theta hat, where this exponent is not very large and negative, then this is essentially equal to 1. Okay. Okay, so now you see that what this tells you is that the posterior distribution on the parameter is expected to be a Gaussian with a variance which is given by the inverse of this gamma. So the variance of theta is going to be essentially 1 over n times gamma. So this distribution here is going to shrink as 1 over square root n times gamma. And so how does this picture generalizes when you have a multidimensional? Imagine that now your vector of parameters is a d-dimensional vector. Then well, then essentially this becomes a matrix. This gamma becomes a matrix, and this becomes a quadratic form, and this becomes a multi-dimensional Gaussian distribution. Okay, and so what you have is that the probability posterior distribution on theta even x is going to be essentially n over 2 pi the d over 2, because you have this integral is a d-dimensional integral, and then you have the square root of the determinant of this matrix gamma, where the matrix say gamma AB of theta is the minus second derivative with respect to theta A and theta B of the log likelihood. And so this here gamma is computed at theta hat, the maximum likelihood estimator, which is always the same, and which is what maximizes the likelihood. And then you have the Gaussian, which is e to the minus n over 2, and then you have theta minus theta hat A times gamma to the minus 1 AB, so gamma AB times theta B minus theta hat B. Okay? So this is just multidimensional gamma. So what does this tell you? Well, it tells you that generally, if you look at the problem in the space of the parameters theta, then here, if you have this is the point theta hat, and now imagine that you are interested in the region where the probability of x of theta given x is larger than epsilon. Then this region here is going to be a region where this quadratic form is less than a certain value. So this quadratic form, I mean, if you draw this region here, this will be essentially an ellipsoid around this point. Let me draw it better. Where essentially the axis of this ellipsoid will be will have a, say, an extension which is proportional to the inverse 1 over the eigenvalues of the matrix gamma. Okay. So so this tells you that essentially if you do this exercise and you compute the maximum likelihood estimators, then the regions where your probability of the parameters is larger than epsilon will be an ellipsoid whose main axes are of the order of 1 over n times lambda, where lambda are the different eigenvalues of the matrix gamma AB. So this tells you that if when you do the fit, you find that there is an eigenvalue which is very, very small, then this will mean that you have one of these directions where the fluctuations in your parameters are very, very large. And this is essentially what happens when you have the phenomenon of overfitting, which is when you have a model that contains too many parameters with respect to the data. In the sense that the error that you have on the parameters becomes very, very large. Okay? So, so indeed, so in general, this in specific applications, so this is a subject that's been discussed at length by a group of people headed by Jim Setner. So what they find is that in many research articles, the models that were used to describe the data contain a lot of parameters, and as a matter of fact, the minimal eigenvalue of this matrix here was so small that there was some direction in the parameter space where the error was completely was very, very large. And they call this, so this direction here is a direction where your probability distribution is very, very flat, because the eigenvalue lambda in this direction is very small. And so these are called what they call sloppy modes. Okay. So another way to see this is that essentially in D dimension, you can see that the covariance between your estimates of the parameters theta A, theta B is essentially equal to the inverse is equal to the inverse of the matrix gamma B computed in theta hat divided by n. Okay, so you see that when the inverse of this matrix becomes very large, then your covariance of the parameters is very large. Okay, so now what I want to discuss is one particular problem, is how much do we learn when we do this experiment. Let's go back to the simple case where we have just one parameter. Okay. So we want to quantify how much, how many bits do we learn when we have a sample of n points and we fit a particular model f of x. So, so the quantity that we learn is actually, you can say it is the mutual information between the sample and the parameter. Okay, so essentially how much the sample tells us about the parameter theta, which is what we a priori don't know. Okay, and essentially you can write down this as the Kuhlmann-Kleiner divergence between the posterior distribution and the prior distribution. Okay, so this is a very simple calculation, and because I remind you that the mutual information is a Kuhlmann-Kleiner divergence between the joint distribution and the distribution which is factorized, and it can also be written in this way. Okay, so this is essentially the expected value of the log of E of theta E of x divided by P0 of theta. Okay. So very good. So we can, now that we have an estimate, so we have an expression for this P0 of x, then we can directly read from there what the results should be. Okay. So and this is essentially, I have the first term is minus 1/2 times log of n over 2 pi. Then I have a term which is, so it's plus 1/2 log n over. Then I have a term which is log of gamma, 1/2 log of gamma. Then I have a term which is minus, so this P0 cancels with this P0, but there is already always a term minus P0 half there, so it's minus 1/2 minus log of P0 of theta hat. And then, so this is, sorry, this is P of theta x bar. And then I have the expected value minus the expected value of the log of, minus the expected value of the log of e to the minus this. which is minus the expected value of say n gamma over 2 times say theta minus theta hat squared. Okay. Now, well, this is just n gamma over 2 times the expected value of theta divided by theta hat, but this is just the variance of theta, which is 1 over n gamma. So this term here is just equal to 1/2. Okay, and so this allows me to write this, to put this 1/2 inside here by just changing this with a e. Okay, add the e here. 1/2 log of 1 over e should be equal to minus 1/2. I'm using that as a model. Okay. So let us look at this result. Actually, this is for one parameter, and let's see the meaning of this. What is the meaning of this formula? Okay, so this part here tells you that essentially you learn is the leading term when n goes to infinity, because these other two terms are finite. Okay, and so this term tells you that essentially you learn 1/2 log n bits. Okay, so indeed, say, if you think about it, so you go from a situation where you have a certain uncertainty on theta to a situation where your uncertainty is awarded 1 over square root n. So essentially you learn 1/2 times log n bits on on your parameter theta, because this is the number of bits that you need to describe a random variable to a precision which is 1 over square root n. Okay? So this is the first term. So then this term is essentially telling you that if the maximum likelihood estimate is a priori very unlikely, it means that this P0 is very small, then you learn a lot. Okay? But if your theta hat is likely, so if this initial probability is large, then you don't learn much. So this term tells you how surprising is the value of theta hat given your prior expectation, okay, or your prior distribution. Okay, so with respect to this term here, this term is related to the curvature of the likelihood as a function of f, as a function of theta. And this is a term that we are going to discuss more in detail, that essentially comes in because it tells you how complex is your model. Okay, so if you generalize this to the case where theta is a d-dimensional vector, then this generalizes in the following way, because essentially now instead of measuring just one parameter, you're measuring d parameters. For each of them, you reduce the uncertainty by a factor square root n. And so this is the term, the gain in information that you get. Then here, instead of this, you have the log of the square root of the determinant of the matrix gamma computed in theta hat. And here again you have minus the log of P0 of theta hat. Okay? Now, what is interesting about this is that this does not tell you anything on whether your model is right or wrong. So it means that you learn these many bits no matter what. Okay? So this actually doesn't even depend on what the model is. For whatever model, you are going to learn these bits. So the information that you learn, I mean, there is nowhere here any information on whether these are the right bits or the wrong bits. The other information is that, say, if you look at the entropy of X, so this is how much information your sample contains. Well, this is proportional to n, because these are n IID random variables. Actually, if they are n IID random variables, then this is precisely equal to n times the entropy of one single random variable. So you see that for large n, the amount of information that the sample contains on the parameters is very, very small. It's only of order log n with respect to n. So there is very, very little information that the sample contains on the models. Okay. Okay. So now what I want to do is to describe all these concepts for a particular class of models that is called the exponential family. So the exponential family of models are models which have this particular form. There is a function q of x which is positive times e to the theta times another function tau of x minus plus some function phi of theta, where this function q of x and tau of x are both positive functions of x, and clearly this phi of x, phi of theta, is the normalization. Ensures normalization. It's given by the normalization. Okay, so this is just q of x times e to the theta times tau of x. Okay, so we have already seen the distribution of this type, in particular when q of x is equal to 1. These are maximum entropy distributions. And these are a very special class of functions, and this is particularly true because if you compute the likelihood over a sample, then this contains three terms. Which is one is just the sum over x of the type of the sample times the log of q of x. So this term is independent of of theta. Then there is a term which is theta times the expected value over the sample of tau of x. And then there is just phi of theta, and this is independent of the sample. Okay. So now, if I compute the gamma, the second derivative of the likelihood, this is the gamma of theta. Then this object, this does not contribute, this does also not contribute. The only term that contributes is just the phi term. This is just minus the second derivative with respect to theta squared of the function phi of theta. And so, by the way, so what is this object? So the first derivative with respect to theta of phi of theta is minus, you see, when I take derivative with respect to theta, I get a tau of x that is going down. So this is essentially the expected value over the distribution theta of tau of x. So this gamma of theta is the form of the derivative of the expected value of theta of tau of x over the distribution P over this distribution here with respect to. So it's a sort of, it's exactly like a response function, okay? At the same point, at the same time, if you take this derivation, this derivative here, then what you get is that this is also equal to the variance, of tau of x over the distribution theta. No? And this is always the same calculation. It's always the same. Please do it, but it's always the same calculation where you take when you take a second derivative, well, because this is essentially a cumulant generating function, and this is and the derivative of cumulant generating function generates the cumulants, which are essentially the second cumulant is the variance. Okay, so what is special about this is that now this second derivative does not depend, it only depends on the data. So when I look at my posterior distribution, then this does not depends on the data, only through the maximum likelihood parameters, because essentially the likelihood, the log likelihood, so this is, if I remind you, this is n gamma of 2 pi e to the minus n gamma of theta hat times theta minus theta hat squared over 2. So this object here does not depend on the data. Okay, it depends only on the parameter. Okay. So So these models are very interesting because the fact that the likelihood, the dependence of the likelihood on the sample only enters through, and so the way in which the likelihood depends on the data only enters through this particular combination tells you that essentially all you need to know in order to estimate theta hat is only the expected value over over the sample of this function tau of x. Okay, you need essentially the equation for theta hat. When you maximize the likelihood, what you have to do is to take the first derivative of this with respect to x, and so the maximization of the likelihood with respect to theta tells you that the expected value over the data of tau plus the derivative of this with respect to theta, which is the expected value over the model of tau, must be equal to 0. So the equation that you have to solve to find the parameter theta only depends on this object here. So only depends on the expected value of tau over the data. So this tells you that all the information about the parameters is contained in this particular combination of the data. Okay, and so these these parameters which have this property are called sufficient statistics. So this object is a sufficient statistics for this particular model. Okay, so let me tell you more precisely what is a sufficient statistics in general. And let's leave these explanation models. So if I learn to discuss sufficient statistics, I should tell you about statistical estimators. So if you have a say parameter theta, like the parameter of this distribution, then you can so the typical statistical problem in estimation is that from this parameter you would you generate a sample from this distribution, and then what you would like to have is a function of the sample which essentially gives you an estimate of this parameter. Okay, so this function here is called an estimator. Okay, and and there are different properties of estimators. So one is that so an estimator is unbiased if the expected value of the estimator is equal to the parameter that I want to estimate. So is consistent if the estimator converges to theta, say in probability as n goes to infinity. So if when I really have an infinite sample, then the estimator really converges to the parameter, and it is efficient if the variance of the estimator is minimal. Okay, so now the problem of characterizing estimator is clearly a problem that is related to which we can get some insight from the point of view of information theory, because you can see that this relation defines the statistical dependencies between these three quantities. And so because of the data processing inequality, what the data processing inequality is that whatever estimator you choose, then the mutual information between say your parameter, your estimator, and the parameter that you want to estimate cannot be larger than the mutual information between theta and the sum. Okay. So then say we define say a sufficient statistics. So T of x is a sufficient statistics if this inequality is saturated. Okay, so this tells you that essentially your parameter, the parameter t, your estimator t, contains all the information that the sample contains on theta. So all the other information besides t of x that the sample contains is not informative about what is the value of this parameter theta. Okay, so how do you how can you make sure that that a particular statistics or a particular combination of the data is a sufficient statistics? Well, because if this is true, then it must also be true that you can write that the statistical dependence can be reversed in the sense that once you know t, if t contains all the information about theta, then you can generate a sample x independently of theta. Okay, so this tells you that if this is true, then it must be that the probability of a sample given t n, given that the sufficient statistics has a certain value and the parameter theta, this should only depend, this should not depend on theta. Okay, so this is called the Fisher factorization theorem. It tells you that if this is true, then T of x is a sufficient statistics for theta. Say, for example, you can check in Bernoulli trials. then my f of x and theta is equal theta to the x 1 minus theta 1 minus x, and x is just either 0 or 1. Okay, so this is the usual Bernoulli triangle. Then if you take the Sn, which is the sum n from 1, I from 1, if you take a sample and then you take just the sum, the number of success of the xi, so this is your estimator, then essentially you can show that this is a sufficient statistics just by using this, okay? Because what is the probability of a sample given, well, the probability of a sample given theta is just theta to the Sn times 1 minus theta to the n minus Sn. This you get quite easily because it's just the product of this, no? So, so you see already from this that the probability of the sample depends on the sample only through the sufficient statistics. So this means that when you write the probability of a sample given that Sn takes a certain value k and you have a certain parameter theta, this you can write it as using base rule. So this is the probability sample and that Sn is equal to k given theta divided by the probability of Sn which is equal to k given theta. Okay, so what is this? So this is just well, the probability of the sample is just theta to the Sn, theta to the k, because Sn is equal to k, and 1 minus theta to the n minus k, times the delta function that tells me that Sn of x must be equal to k, divided by, well, this is just the binomial distribution. This is just n choose k, theta to the k, 1 minus theta, n minus k. So what you see is that this part and this part essentially cancel, and you only have that this distribution here actually does not depend on theta. So essentially this is a sufficient statistics for Bernoulli trials. Okay? Very good. So now, so essentially in exponential models, this tau of x is clearly, you can do the same argument here and show that essentially tau of x is a sufficient statistics in this particular model.